Hello there, my name is Enrique Dominguez Carcamo, and I am a junior at UNC Greensboro, and today I will be presenting my poster for this year's Virtual Expo titled Novel Method of Heterogeneous Catalysis, Self-Assembled Monolayers, or SAMs. I do undergraduate research with Dr. Kimberly Petersen, who is in the Department of Chemistry and Biochemistry. So to get started with the introduction, self-assembly is a highly effective and versatile strategy for surface functionalization, which is basically building blocks. They build upon each other. Self-assembled monolayers are usually formed on semiconductor metal surfaces, which for this project we will be using a gold metal surface. In the Petersen lab, we're attempting to introduce a chiral catalyst into this self-assembled monolayer, which will be formed again on a gold surface, and the environment will be heterogeneous, which basically means that the SAMs will be in a solid form, and the substrate that were introduced in the chiral substrate will be in solution in liquid form. We expect and hope that this will make it easier to extract the SAMs and reuse it for other work, which will not only make it time efficient but also cost efficient, which is very important for anything in the scientific arena. So to get into the background, again, we're introducing a chiral catalyst into the self-assembled monolayer, which a chiral catalyst, if you look at the figure down below, you have two pictures that look identical. But if you look at the left picture with the dashes and the right picture with the wedge, that is known as an inversion center, which totally changes the reactivity of the compound. The left figure smells like oranges and the right figure smells like lemons. Now, these are two totally different smells, and this is all due just because of an inversion center. And this is what we mean by we are going to introduce a chiral catalyst and see how the SAMs will react. Getting into the methodology, so this project required collaboration with graduate students in the Petersen lab and Dr. Petersen herself. Most of the reactions were performed under air and moisture-free conditions due to the sensitivity of these compounds to water. Argon gas, vacuuming, and flame drying were used to create this moisture-free atmosphere. With the assistance of various techniques and instruments such as an NMR machine, column chromatography, I was able to perform these critical experiments for this project. My part, which is shown in figure 1, the figure down below, titled Reactions Pertaining to the SAMS project that I have carried out in the Petersen lab. This consisted of 3 reactions. Substrate 1, diterbutamalonate, was my starter material. It was alkylated by the pink reagent to form compound 2, which had the second reaction of substrate 2 react with the blue compound methyl iodide, which ended with a methyl group forming substrate 3. The last reaction has substrate 3 react with K2CO3 and methanol and revealing the free OH group, an alcohol group. This forms substrate 4, and this is the material that will undergo the catalysis by the SAMs, the chiral catalyst that will be introduced with the SAM. Now the SAMs are going to be prepared by graduate student Josh Frost. Now for future work, if this project is successful and the self-assembled monolayers do in fact display the outcomes that are predicted by the Petersen lab, then more chiral substrates could be introduced to the SAMs. This could provide an endless amount of data on the reactivity of the self-assembled monolayers with countless chiral substrates. Other metal surfaces could also be used and see how that would change the reactivity, what outcomes, different outcomes it could produce. So to conclude, work has already been done with the substrate I synthesized in the Petersen lab, but it was done with the TRIP catalyst, which is a massive molecule, and it is not a self-assembled monolayer. Now, if you look at the picture down below, that is essentially what we're doing. That is the substrate I synthesized, substrate 4, but it was done with the TRIP catalyst. And like I said, we expect if we introduce the SAMs into this chiral environment, which is in heterogeneous solution, that we will be able to extract the SAMs and reuse it, which will decrease not only time, but cost. So all this, as an undergraduate student, the process has been difficult, but it has been rewarding. I am very thankful for the opportunity to do research with Dr. Kimberly Petersen. She is an amazing instructor. This has all been very exciting, and I hope this continues forwards. And I greatly appreciate the opportunity to present my work, and thank you.